Kinesiology of the musculoskeletal system, Chapter 4, Biomechanics. Chapter overview. First thing we're going to do is review Newton's three laws of motion: inertia, acceleration, and equal and opposite reaction. Then we're going to work on analyzing muscle forces, torques, and joint reaction forces using free body diagrams and axes, by calculating collinear and nonlinear loads, calculating internal and external torques, determining muscle force, determining joint reaction force. And we're going to use our problems 1 through 3 in the book as our examples so you can carefully follow along. There's a lot of detail in these pages and some math to do as well. One of the things you're going to need for this class, if you don't already have one, is a calculator that has some scientific functions such as sines and cosines or trigonometry functions. Okay, so the first of Newton's laws of motion is the law of inertia. And inertia is essentially the resistance to change. So you've heard this before: a body remains at rest or motion until a force compels it to change. So for our example here, you can see the person's about to flick the cardboard box or card out of the way, creating motion of the card through an external force. And then the coin will drop into the tumbler, right? So until something compels these objects to move, they will not move. The tumbler will not move because there will not be sufficient force by flicking the card out of the way to create enough change to affect its inertia. So a body remains at rest or motion until a force compels it to change. There are two types of equilibrium that we should discuss when talking about inertia. And these are static and dynamic equilibrium. So during static equilibrium, the body has no rotational or linear velocity. It is still. It is at rest. So linear, of course, is a straight line more or less, and it's defined by force. Okay? Rotational velocity is created by torque. So rotational is torque, linear is force. That's something that you'll hear throughout this chapter and probably the remainder of the book. Dynamic equilibrium is a little bit different. This is when rotational and linear forces are not zero, but are constant. So for example, if you're driving your car in cruise control down the freeway at 60 miles per hour, the car is in dynamic equilibrium. So it's not zero, but it is constant. So in this example on the left, we have a gentleman filling up his car, and on the right, a gentleman driving the car. So what force is overcoming static equilibrium? Where is the torque producing rotational velocity? What is causing linear displacement of the car? In this case, is rotational and linear dynamic equilibrium proportional? In other words, if we increase rotational velocity by 20%, do we also increase linear distance 20%? Or is it different? So what force is overcoming static equilibrium? Well, when we put our foot on the gas pedal, energy put into an internal combustion engine is what creates that force, right? Through the drive shaft to the tires. So where is torque producing rotational velocity? Torque is produced through the drive shaft to the tires, and those tires are driven by rotational velocity. And what is causing linear displacement of the car? The rotational velocity of the tires, right? So it's much the same with a person. When we do gait, for example, and walk or run, we use torque created through a muscle force to linearly displace our body to where we want to go. In this case, is rotational linear dynamic equilibrium proportional? Yes. In other words, if the tires turn 20% faster, then our linear distance is going to be 20% further. So in this case, the answer is absolutely yes. Okay, so looking at the example of our car, to maintain static equilibrium of the car, how would lighter material of the car affect its efficiency? Well, inertia is proportional to mass. So if the car were made of lighter materials, of course, then there'd be less inertia, right? So the car would go faster. How about tire pressure? If the cars are under-deflated by 50%, there'll be a higher coefficient of friction and inertia of the tires through the earth, right? So it's going to slow down. How about the number of people in the car? It will slow down. Will require more energy to maintain that dynamic equilibrium, right? How about the size of the tire? Here it's a little tricky. You would think perhaps that because the diameter of the tire is larger, that we could gain more distance for every turn of the crankshaft. And while that's true, it does not account for the increased size and width of the tire, which increases the overall weight of the car and increased friction through the pavement. So here's a couple of fun facts for rotational velocity and linear displacement. For a car traveling at a linear velocity of 60 miles per hour, the tire spins at 812 revolutions per minute, or 13.5 revolutions per second. This translates to 4,860 degrees per second of angular velocity. That's rotational velocity. So at 30 miles per gallon in fuel efficiency, the tire does a complete revolution about 24,360 times. That means that at $2 per gallon, 8,769,600 degrees of rotation are achieved, or 43,843 degrees per penny. That is the overall cost or energy to overcome friction of the tires on the ground and gravity. So let's look at our rocket ship on the right. The first one is docked and ready to take off, and the second one is probably very close to or in space. So which one is going to require the greatest amount of energy, obviously, to increase its linear velocity? Well, clearly the one on the ground, because it's affected by gravity. Moreover, it's at rest. So it has to overcome that initial inertia. Our rocket ship on the bottom is already in motion, right? So in order to maintain dynamic equilibrium, it requires much less energy input. In fact, the higher it goes until it is actually into space, progressively less energy is required to maintain the same velocity. Inertia and human movement. Rotational and linear velocity are dependent upon our body's center of mass. So, key point here is looking at this picture and seeing that the black dots on the picture represent the center of gravity for the various components of the lower leg. Okay? So the top one on the right leg shows the femur. So that's the center of gravity for the femur. And then we have the center of gravity for the tibia portion of the leg, sometimes called the shank, S-H-A-N-K. And then we have the center of gravity for the foot. So the red dot is a composite center of mass for the entire lower extremity. It lies here just above the condyles. However, the left leg looks like perhaps they're doing a calf stretch or they're getting ready to run. The left leg, you'll notice that the center of mass for each component of the body, the thigh, the shank, and the foot, are identical. However, if we look at the red dot, we'll see that the center of mass has moved outside the body and actually behind the knee. What that's going to do is create a decrease in the limb's mass moment of inertia and allow the leg to come forward with greater velocity, let's say if they're running, and less effort than if you were running with your legs straight. So here's a picture of a diver. So we know that in the anatomical position, center of mass is essentially anterior to S2, right? So you'll see there are 3 dots representing 3 different positions of the body as they go through the process of diving off the board. In the first, they're more or less straight up and down, so the dot is perhaps a little bit more forward than just anterior to S2. But when they start bending backwards in the second dot, shown by the green arrow, the center of mass appears to be somewhere around the position of the spinous process of the lumbar spine. And then, in the third one, the highest one, if you will, the highest blue dot, we see that they're bending backwards even more, and the center of mass has actually moved outside the body. So this is important to understand for sport activity, for daily function, and for all types of things. I'll give you an example here. So here's an example of the basic positions that are used in diving. On the left, we see that this is a straight position. These 3 are called straight. Different positions of the body, for sure, but nevertheless straight. Which one of these 3 do you think most represents anatomical position? Well, probably this one, right? Where would the center of mass change in this individual? Would it be higher or lower? Anterior or posterior? Probably a little higher, right? And a little bit posterior, right? And we're not sure how much this person is bending backwards, but it's probably not going to be as high as this one because both of her arms are over her head here. So which one is going to spin the fastest? This one, or this one? And why? Well, it's going to be this one because they have made themselves as small as possible. Here, with the arm out to the side, they've created more inertia. And here, with both arms up, they've created a great deal more inertia. So if they're spinning in the air, they can't turn very fast. Right? So that's a straight position. Then we have our pike position over here. Right? So which of these 3 has the center of mass within the body, do you think? Probably none of them, right? None of these have their center of mass inside the body because of the position. It's probably somewhere in front of their hip, anteriorly, let's say in this area, right? Which one is going to create the most angular velocity because their inertia is the lowest of these 3? Probably this one, right? Because they're balled up, if you will, more so than these 2, right? The tighter she is, the more it looks like tuck position over here, the faster they're going to spin. How about between these two? Well, probably this one would be next, and this one would be the slowest, right? This one, she's going to spin more slowly. This one, a little faster. This one, even faster, right? And finally, we get to the tuck position, where the center of mass is somewhere inside of her because she's balled herself up so much. It could be at the position where the thigh meets the trunk, somewhere in there, right? Somewhere. But because the mass moment of inertia here is lower, she's going to spin much faster. So mass moment of inertia is essentially what the distribution of mass is around the center of mass. So here, the distribution is quite tight. Here, not as tight. Here, least tight, or really not tight at all. So fastest, intermediate speed, slow speed. Consider a runner. When a person executes the swing phase of running, they flex the knee and hip to decrease the limb's mass moment of inertia and allow the leg to come forward with greater velocity and less effort. In other words, it's more efficient. It's like our tuck position, right? The mass moment of inertia is smaller because the knee and hip are flexed. So let's take a look at this video. Here's a picture of a man running for unknown reasons with his legs straight. Imagine being out on the track and trying to run with your legs straight and racing against somebody that could bend their knees. It wouldn't be a fair fight, right? Because as the legs stay straight, the mass moment of inertia of the lower extremities is that much greater, right? So they're going to be unable to run very quickly. Compare that to the greatest sprinter probably of all time, Usain Bolt. So let's take a look at this video. Notice how quickly he gets his lower extremity into the minimum mass moment of inertia position. By the time his knee gets just anterior to his hip, he is in full tuck position. Try to watch a couple of the other runners and when their knee becomes maximally tucked. It's a little bit later. So he can probably run the fastest because he's able to get into that minimalized mass moment of inertia position more quickly, and he's freaking tall. He's 6'5". So he takes actually 3 or 4 fewer strides than his competitors, okay, when he runs the race. Finally, let's take a look at this last video of a person doing a spin in skating. And this is fantastic, of course, because there's such little friction coefficient going on because of the ice skates. There's a dramatic change in the velocity of spin depending on how tight the person is able to make themselves. So just take a look at this and just enjoy it.
Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When the skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases.
The next of Newton's laws is the law of acceleration. Now, before I go on, I want you to take a look at table 4.2. So the definitions here in this table are important. I want you to know them. Definitions, particularly for linear and rotational application. So you will notice that for some of the parameters on the left, there is no defined relationship for rotation or linear application. So I just want you to know these and understand what those different components symbolize, because they're important to understand for the rest of the chapter and going forward in the text. So there are essentially three ways to study acceleration, and that is looking at it from three different positions. One is a force-acceleration relationship, two is an impulse-moment relationship, and three is a work-energy relationship. So of course these are all inertia and mass dependent, of course. So if we have the force here at the arrow, they're identical. If this arrow was longer, that would mean that the force was greater. If the arrow were shorter, it would mean that the force was less. So we see that if we give the same amount of force to, let's say, a tin can as we do to an automobile, one is going to be moved with a much higher, greater velocity than the other. Of course, the can will be pushed forward at a much higher acceleration rate than the car will. So force-acceleration relationship is proportional to the force applied in the same direction as we've seen already, and inversely proportional in mass, as we see with the example of the tin can and the car. So when we want to change dynamic equilibrium, we're driving down the freeway at 60 miles per hour. If we want to speed up, we're going to have to increase our energy, right? So if we look at the difference between a moped and an SUV, of course, we're going to require less energy to change our dynamic equilibrium than we will with the SUV. Less energy for the moped, more energy, of course, for the SUV. And we can also change our dynamic equilibrium by, of course, taking our gas off the pedal. And then we're going to slow down due to inertia and friction. So that's not really an acceleration relationship, it's a deceleration relationship. But do understand that it's proportional force and inversely proportional to mass. So why is this important? Well, let's take a look at a jump ball in basketball. At the beginning of every game, we have the two players facing each other. The official throws the ball up into the air, and the players jump to try to tip it to one of their teammates to see who gets the first chance to score, right? So let's say we're in this situation and we're doing a jump ball and we want to know who's going to win. There are going to be several factors that go into play here, right? One is height. Assuming everything being equal, the taller person is going to win. One is weight. Assuming equal in everything else, which one do you think is going to jump more quickly? The person that's lighter, right? Arm length, the one whose arm is longer. Timing, well, the fastest and strongest and biggest guy, if his timing is wrong, will lose the tip. And of course the toss, which we're going to assume is equal. What if all these were equal? Okay, height, weight, arm length, timing, and toss. Everything is equal. Who is going to win the jump ball? Well, it's going to be that person who is able to create the highest degree of acceleration, force acceleration through his muscles. The second way we'll look at acceleration is through impulse-momentum relationship. This is a relationship that's expressed in time. So it's a quantity of motion in kilograms per meters per second. So when we go to change our momentum, whether it's from static or dynamic equilibrium position, that impulse is going to be caused by an input of energy that may speed up or slow down that particular body. So let's go back to our car example. So let's think about our impulse as either pushing on the gas accelerator, right, or stepping on the brake. The input of energy then may speed up or slow down the car. So we have two types, really, of impulse here at their extremes. We have a low, slow impulse, all right, and we have a high, fast impulse. So let's say we're driving down Montana Avenue on the east side of El Paso, and we're coming up to a stoplight, and we can see the stoplight is turning red, and we know we're going to have to stop. Well, we can use our slow, low impulse to gently take the car from 60 miles per hour to 0, right? Now, on the other hand, let's say we're driving on Montana Avenue at 60 miles per hour, and somebody pulls out in front of us inappropriately, and we have to slam on the brakes. That would be a fast impulse or high impulse, fast duration, right? So here, again, the impulse momentum relationship is expressed in time. So the amount of time and the quantity, really the quantity of the force or impulse over a given time. So if we were driving 30 miles per hour and wanted to go to 0, we could probably do so in a couple of seconds. But if we're going 80 miles per hour, it's going to take us 6 seconds, let's say. So the important thing here to remember is that with impulse-momentum relationship, it's an expression of time. What about functionally? Now, because it is a reflection of time, there are going to be different circumstances that call for a high or low impulse. So in our two examples here, we have a woman putting back a rebound. So somebody shot the ball from her team, missed the shot. This woman in pink grabbed the ball and is putting it back up for a score. This gentleman over here jumped up on the box, presumably, or stepped, and then jumped off the box and lands. Which one is it going to be more advantageous to have a slow or a longer impulse momentum relationship function? Well, it's going to be this guy, right? Because if he jumps off of this 12-inch box and lands abruptly with his knees more or less straight, he is at increased risk of hurting his knees. Correct? On the other hand, this gal over here, if she uses a slow impulse to put the ball back up into the basket, then she risks these players in black to defend her and for her not to score, right? So sometimes we want a quick impulse, like going up for a rebound and putting it back in, and sometimes we need a slow impulse. So those are just two examples of the impulse-momentum relationship. And that's very important in safety. So consider a bicycle helmet. This is supposedly one of the best on the market, this Hero, H-G-I-R-O helmet, right? So it has some interesting design in it that protect us from getting injured. And when we fall or hit something, when we're riding a bicycle, then of course our helmet is going to protect our head. It's not just a physical barrier, however. A physical barrier could also be a plastic bag over our head, but it's not going to have the design elements in it that decrease the force to our brain. So here, the helmet essentially increases the impulse momentum, right? It increases the length of time the impulse is taking place, or the load is taking place to the head, right? So if we're not using a helmet, we're going to hit the ground with our noggin and we're going to experience the blow instantaneously. However, with this, even though it's only like 2 or 3 milliseconds of time, the bicycle helmet transfers much of that energy to itself and decreases or delays the impulse to the brain through its internal mechanisms and technology. So what I'd like you to do is take a moment, copy this video right here, this YouTube video, and watch this. And you'll probably never look at bicycle helmets the same. It's really very fascinating. They actually use some of the nomenclature that we're using in the biomechanics chapter here to discuss what happens. So pause the video for a moment and go to this video. Copy this video, put it into a browser, and watch. The third way we look at acceleration through work-energy relationships. Now, work, as we know from the past, is force times linear displacement of an object. It is not time dependent, however. It's important to remember that. It has nothing to do with time. Work does not mean time. Here, we're talking about just straight up newtons. So force times linear displacement. So here we see that the force that this gentleman is applying to the sled is 50, and we're going a distance of 30 meters. So what would that be? Well, that would be 150 newton meters, right? However, this is an excellent place to start introducing our upcoming problem-solving exercises from the trigonometry. So the picture of the man pulling the sled is using a force of 50 newtons, all right? But consider, what is the angle of pull? It's 30 degrees off of the most efficient axis, right? So if he was down in this position pulling, then we would get a true sense of how much force it actually takes to move the sled. But because he's pulling at a 30-degree angle, all right, we have to adjust for the actual amount of force that it takes to move the sled. So because the man is not pulling at the optimal position, does the force that is required to move the sled, is it less or more than 50? Well, clearly it's going to be less. How much less? It depends on the angle, right? So here's just a time that we can introduce our trigonometry functions with sine and cosine. So we're going to use a sine of 60 here to represent a percentage of the force that is actually required to pull the sled. So a sine of 60 is 0.866. That's the percentage. So it's 86.6% of the force if it were in an optimized position. So if you take a sine of 60, multiply times 50, we get 43.3 newtons of force. That's the true force that's required to pull the sled. And then if we multiply that times 30, we actually get 1,299 newton meters, okay? Instead of 1,500 newton meters that might be assumed because of the number here. So just remember that the angle of pull is going to have a great deal of influence on the actual force being produced. We're going to see that a lot more in our upcoming problems. So let's think about this picture for a moment. What if we lengthened the handle by 2 times? Would the newton meters here change? No, it would not, because we already know it takes 43.3 newton meters to pull it, times 30 meters is 1,290. That's not going to change. However, the efficiency is going to increase or decrease, and why? Well, it's going to increase because when this is longer, and we're going to assume he's walking along, his arm length hasn't changed, his leg length hasn't changed, so he's going to be pulling this, it's double the length, probably more along this angle, maybe closer to 15 degrees. So we would take a sine of 75, which means that he would probably only be using perhaps around 47 newtons of force. What if the handle was shorter? Well, he would be pulling at a higher angle unless he squatted down, right? Which would make him more or less efficient. It would make him less efficient, which would do what to this number? It would increase this number, right? And it's going to lower our sine. So if this was half as long, perhaps this would go to a sine of maybe 50, let's say. And the resultant force is always going to be the same because that's the amount of force it actually takes in the optimal axis. But it will be less efficient for him. What if the man was shorter? It would be more efficient, right? If the man is taller, it would be less efficient. So just things to think about as we go forward. All right. So when we talk about work-energy relationship, we have to know about energy. And that is potential energy and kinetic energy. So here's some examples of potential energy. Now, the important thing to remember is that potential energy is energy that is possible for an object that is at static equilibrium. So let's look at our pictures here. We have a hippopotamus and we have a giraffe. Now, in real life, the giraffe is much heavier than the hippopotamus, but hang with me. So potential energy is a function of height under gravity. Assuming that the giraffe and the hippopotamus were the same mass, which one would have the highest potential energy? Which one would cause the most potential damage or force to the earth if they fell over? If you want to think about it that way. It would be the giraffe, right? So that old expression, the bigger they are, the harder they fall, is very true. If we have a man that's 6'4" versus a woman that's 5'1", the man is going to have higher potential energy because it's a function of height under gravity. Moreover, the man is heavier probably, most likely, so their potential energy is going to be the greatest. So that is true when we're talking about height under gravity internally, like inside these animals, and also externally. So let's look at this picture I found of a bunch of cats on a ladder. All right, so here's the cats on the ladder, and we have 1, 2, 3, 5 cats. Let's say they all weigh the same mass. They all have the same mass. Which cat has the highest potential energy? Of course, it's going to be the cat on top. And the cat with the lowest potential energy is going to be here, right? So, assuming the same mass, potential energy is going to increase the higher from the ground the object becomes. Okay, so as opposed to potential energy, we also have kinetic energy, which is just essentially the same as momentum. So it's influenced by mass and velocity regardless of gravity. And potential energy is able to be converted to kinetic energy as it falls. So looking at the picture of our cat on a ladder, they have potential energy. If the middle one jumps off, now they are using or experiencing kinetic energy, right, as they fall to the floor. Our picture here on the right, okay, is under gravity. This one is not, but they're both kinetic energy, okay? This, we use a force to push this box. There's no gravity. Well, there's gravity of the box, but there's no gravity like we see here on the hill. it's going to stay the same throughout the distance, right? So we're going to push this box, and we have kinetic energy. Here, we have somebody going up a hill using his bicycle. At the top, he stops, has a drink of water, has a granola bar, he has potential energy. And then when he rolls off, he has kinetic energy once again. All right, so remember we said that in work, there is no parameter of time that we're worried about. So how do we introduce the element of time? We use the term power. Power is the rate at which work is done. So let's go back to our example of this gentleman here. Just to review, he's pulling the sled using 50 newtons of force for 30 meters. That's an internal energy to him of essentially 1,500 newton meters. That's how much work that he's done internally to himself. However, external work, the amount that it takes to pull the sled, as we discovered before, is 1,299 newton meters. So let's introduce our element of time. So in traveling 30 meters, let's say he does that very quickly, in 5 seconds. That would be very fast. Then the power would be 1,299 newton meters divided by 5 seconds, which would be 259.8 newton meters per second. That's a high degree of power. Let's say, on the other hand, he does it in 10 seconds. Well, now, power is halved, right? 129.9 newton meters per second, because it's taken in 10 seconds. What if it took him 20 seconds? Well, it would be half of this. It would be essentially 65 newton meters per second. So power is the rate at which work is performed. So understand those relationships. Work is just simply newton meters, where power is newton meters per second. You'll want to remember that. Okay, and we get on to our final Newton law, which is the law of action-reaction, or equal and opposite reaction. So here it states that for every action there's an equal and opposite reaction. Anyone that's married knows this. Anyone that's dating seriously knows this. Anyone that grew up in a family knows this. So we all know this. So let's take a look at the boy pulling a rope on the telephone pole. The resistance to inertia of the telephone pole is very high. We could get 10 people over there to pull on it, and it's not going to move, right? However, if we took a car and smashed into it at 80 miles per hour, I'm guessing there might be some movement, right? But here, our boy is pulling, let's say, at 50 newtons, and this is just static, so the boy is pulling at 50 newtons, and essentially the telephone pole is pulling at 50 newtons, right? Equal and opposite reaction. How about in a dynamic relationship? Here, the boy is pulling against an elephant. Now, let's say the boy is pulling at 50 newtons at his maximum, and the elephant is pulling at 50 newtons, which means he's probably displacing his center of mass back about 0.1 inches, right? He's leaning back very so slightly because he's hardly using any of his true power, right? So here, equal and opposite reaction. The boy pulls and the elephant pulls, and this doesn't move. So what happens if the elephant pulls more? Let's say he produces a force of 100 newtons. So now that excess energy is going to be converted into kinetic energy. In other words, the boy will fly to the right, right? So equal and opposite reaction, still the same, however, because the elephant is still exerting 50 newtons of force on the boy, and the boy is still exerting 50 newtons of force on the elephant. But because the elephant is producing 100 newtons of force, then that excess 50 newtons is transferred to kinetic energy. All right, so here's our rocket ship. So for every action, there's an equal opposite reaction. So the engine produces a force, and that external force is coming out the tailpipe, more or less. So in other words, it's a thrust. And that's going to propel the rocket ship forward. So if we have a very small amount of energy come out back here, then we can expect the rocket ship to be propelled forward at a relatively lower amount than if this was a greater force. And that's true regardless of if they're in space or if they're between the ground and space itself. Okay, so now we get onto the nitty-gritty detail of the chapter, and that's looking at formal analysis of forces. I use that term loosely, okay? Because in reality, remember, force is a function of linearity, right? Linear forces, rotational torque, right? So here's a formal analysis of forces and torques. I just put forces. Part 1. First thing we're going to want to do is construct, or be able to construct, a free body diagram for the biceps and the quadriceps using page 86, steps in constructing the free body diagram. So we're going to look at that. And then we're going to learn how to calculate collinear loads, which is very simple. We're going to look at how to use a polygon method to determine coplanar forces, in this case for the hip abductors in a static stance position. And then finally we're going to calculate force from manual resistance using force and lever arm and see what those relationships are. So here's an example of a simple free body diagram. You can see in the picture here that we have, let's move that out of the way for a minute. We have a picture of a person's humerus, biceps, triceps, radius, forearm, and hand, right? So in this simple free body diagram, we have, you can see here, different lever arms and different force components. So we have to account for all of these, okay? We need to figure out where the axis of rotation is. So where is the axis of rotation in a given joint? Do you remember? Is it within the convex or the concave member of the joint? It's in the convex member, right? So for the glenohumeral joint, it's within the humerus. For the tibiofemoral joint, it's within the femur, right? So the axis of rotation, as shown here by this dot right here, is within the convex member. All right? So after figuring out our axis of rotation, we want to look at the weight and the center of gravity of the limb. So forget about the book for a moment. We're just looking at this, forearm and hand. Well, we can see here that the forearm and hand component weigh 2.5 kilograms, and it's sitting at what appears to be 18 centimeters from the center of, or the axis of rotation here. So then we need to draw in our weight and center of gravity, or center of mass, for our external load. So here's our external load being the component of the forearm and hand, and then our external load being the book. So here it weighs 4 kilograms, and it's sitting at 30 some odd centimeters from the axis of rotation. So these are the things we need to draw in for our simple body diagram. So our internal moment arm, and this is super important, internal moment arm is the distance between the insertion of the tendon into the bone from the axis of rotation. So that is going to be short. Here it shows 4 centimeters. That's our internal moment arm. Then we look at our external moment arms. Well, we know our external moment arm has to be figured for 2 components, our forearm and hand component and our external weight component, right? So there we put it here and there we put it here. And then we need to figure out the angle of muscle application. So in this instance, it is 90 degrees. That's the degree of the forearm, okay? The biceps in the anatomical position is in a vertical position, right? Which means when we get down to the radial tubercle on the radius insertion, it's going to be at a 90-degree angle from this axis here, from the axis of rotation. And finally, we need to add our x and y axes. So this is really important. Understand that for this book, we're using something called the right-hand rule, okay? So you're not going to see this type of diagram facing in the opposite direction. You're going to see this for the biceps. You're going to see this for the quadriceps. You're going to see the right thigh extending the lower leg this way. Because for the purposes of biomechanics, we put things in a right-hand rule. So just understand that the x-axis, okay, very important, the x-axis goes along the mobile component of the joint. Which is the mobile component? The humerus or the radius? The arm or the forearm? Well, of course, it's the forearm. So the x-axis in this situation is along the radius towards the hand. And the y-axis then, by definition, is 90 degrees counterclockwise from the x-axis. Okay? And the arrow of the x-axis points down the axis of the mobile segment. So it's important to understand, super important, that the arrow represents positive. Okay? So anything that occurs in this direction along the axis in the direction of the arrow is going to be positive. So as we hold the book here with our biceps, it's a positive force. The biceps is acting in a positive direction. The book is acting in a negative direction on the y-axis because gravity, right? That's why this arrow here is pointed down. So that's a negative force. This is a positive force. This is a positive force. This way would be a negative force. So that'll be super important as we go through our examples. So let's look at our example in figure 4.22, page 91. In this example, we have a picture of somebody performing a long arc quad using the quadriceps in a sitting position. Okay? So let's take a look at figure 4.12b. That's the one, that's the free body diagram on the right. And you'll see that we have all kinds of colors and all kinds of arrows. We're going to try to make sense of those. So let's look for the axis of rotation within the joint. Where is it? Well, it's the little white arrow that's being pointed to by J. Right? That's the axis of rotation. How about the weight and center of gravity for the limb? Well, that's represented by the black arrow. And the nomenclature used in the book here is S. Okay, so S is the weight of the shank. Remember we said the lower leg can be termed the shank. So S in this case is the shank, the lower leg. That is the position where the center of mass lies. So we can see that S, pointed straight down with that black arrow, is in a negative direction because it's being influenced by gravity. Now let's look at weight. Its center of mass, or gravity, and external load. So here we have the weight, signified by W, right? So here W, again, it's a downwardly pointed arrow because that's the line of gravity. You'll see that Wx is moving down away from the knee, and Wy is moving in a negative direction. How do we know it's negative? Let's take a moment and look at the XY axis on the right side of the diagram. We can see that the X is going down the long arm of the mobile segment, the tibia, right? We know that's how it works. And the Y-axis is 90 degrees counterclockwise from that, right? So look at Y and X, and we'll see that Y is pointed essentially at a 45-degree angle from the horizontal position up and to the right. Look at SY. It is pointed in the exact opposite direction of Y, right? S is the shank, and SX is the direction of X. So SY is going to be negative because it's going against Y, which is positive. The arrow direction is pointing up in the picture on the right for the y-axis, and the line SY is pointed away from that, so it's a negative number. Okay, now, internal and external moment arm. Where is the internal moment arm? It is going from the insertion of the quadriceps to the axis of rotation. So it doesn't give us what it is here, but we know where it is. And then the external moment arm is the distance from the axis of rotation to the center of mass for the shank. And the external moment arm for the weight is the distance from the axis of rotation of the knee to the weight itself, right? All right, so that kind of gives you an idea of free body diagram, and you can go back to that steps in constructing a free body diagram, page 86 for clarification. All right, so let's get on to something a little bit easier for a moment. Analysis of forces, calculating co-linear forces. When we talk about co, we're meaning together, right? Like co-worker, things like that. So here are two examples of co-linear forces. All right? Collinear in this aspect refers to the pull of force or torque. So in the example of the woman carrying water on her head, this collinear force is additive, right? Her body weight and the water, if she's standing in a static position, all are going to the earth at the same degree. It's a collinear force. On the other hand, the gentleman here at the bottom using an unweighted walking device has the weight of gravity pushing down on his body, but is being unloaded by this contraption here around a harness and giving him some counterforce so that there's not as much weight on his body when he walks. Now that can be really useful if you have, let's say, a cartilage procedure on your ankle. Walking here is going to be much more comfortable and less potentially damaging than walking without, because there's going to be much less load. Now we achieve the same thing by walking in the water, of course. So let's look at page 88 for a couple of clinical examples. Figure 4.8. All right, so the picture on the left, figure 4.8a, we see that the shank, the lower leg, is pointed is pointed straight down towards the floor. So it's just the load of the lower leg and foot. Moreover, the weight on the foot is also pushing straight down towards the floor. So those are examples of collinear forces, where the shank weighs 40 newtons and y negative. Well, you can see from the XY diagram that the weight of the leg and the weight of the object are going in the opposite direction of the arrow. So therefore it's a negative number. The weight is minus 44 newtons for the same reason. Those are collinear forces adding up to negative 84 newtons. Let's look at B. So here we have an example of sitting traction. So this can be done in the clinic, it can be done at home for people with foraminal stenosis, disc problems, and so forth of the cervical spine. Here we have the weight of the head of minus 53 newtons. And it's negative again because of gravity. It's pointing in the opposite direction of the arrow in Y. Okay? And then we have a traction force of 75 newtons. It is going up. The green arrow is going up. That's in the direction of the Y arrow, therefore it's a positive number. That is a collinear force because they're occurring in the same angle. And what is the final force then? Well, it's 22 in a positive direction. The resultant force is T, traction force, minus H, the head force. So that is really as simple as you can get for collinear forces. Very simple concept. All right, so analysis of forces, analyzing coplanar forces using a polygon method. This can get quite interesting from a biomechanics standpoint. A lot going on here, but all I want you to be able to do is think through the process. So we're going to look at the next page there, page 89, figure 4.9 for a clinical example, using joint reaction forces. So in this picture, we have somebody who's had a total hip replacement. We want less joint reaction force because it's going to be easier on the prosthetic and it's going to give them more miles, essentially, in the joint. Okay? So let's look at what they're talking about here. We have a red line, a black line, and a blue line, where the black line indicates the weight of the body. The red line is the muscle force, and the blue line is joint reaction force. The red line is the gluteus medius. Let's just ignore the other muscles for a moment because that's the main one. The black line is the body weight. So this is in single leg stance. So the weight is equal to the weight of the individual. Okay? Its length represents the weight of the individual. The length of the red line is M. That's the amount of force it takes to keep them from falling over. And the resultant reaction force is R. So let's play around with this a little bit. Let's move the origin of the gluteus medius a little more medially. What happens to joint reaction force? Let's look at that. Would it increase the joint reaction force or decrease the joint reaction force? Well, if the origin were moved medially, then the angle of the color M line would be greater, right? So let's just assume W is the same and assume the joint reaction force line is the same. If we change that angle, we would get a smaller joint reaction force, right? Does that make sense? So we're going to put the R tip to tip from the W, okay? So given the amount of weight in the black line and given the amount of muscle force in the red line, the joint reaction force is calculated, okay? If we took that blue line and extended it down to the bottom of the page, it could happen anywhere along that line, okay? Does that make sense? So for example, if we move the origin of the gluteus medius laterally, then it would essentially decrease the angle of M. So if we decrease the angle of M and put the tail of the red line at the head of the black line, then it would not touch the blue line until further down the page. Does that make sense? Therefore, the resultant joint reaction force would actually be greater. Okay? How about if we move the insertion medially? What would happen then? We move the insertion on the greater tuberosity medial. We move it medial, what's going to happen? Same thing, right? Same as moving the origin laterally. It's going to decrease that angle. It's going to cause it to run into that blue line at a later time. Okay? So the resultant joint reaction force is going to increase. And of course, if we move it laterally, if we move the insertion laterally, then the angle is going to increase, and therefore it's going to run into the blue line more rapidly, which means that the resultant joint reaction force is going to be less. What if we ask the person to lose 30 pounds? What will happen to the black arrow? It will decrease in length. Assuming the same muscle force, what will happen to the joint reaction force? It will be less, right? If we take and we move the black arrow, make it shorter, and have the same angle of the red line, it's going to run into that blue line more quickly, which means the joint reaction force is going to be less, and that makes a lot of sense. However, if they gain 50 pounds, then the length of W is going to be longer, and it's going to run into, the red line is then going to run into the blue line later, which is going to cause the joint reaction force to be higher, right? Okay, now what happens if we side bend the spine to the right? Okay, so we're standing on our right leg. What happens if we side bend our spine to the right? What effect will that have on our joint reaction force? Well, it's going to take our W dot and move it to the right or left. It's going to move it to the right, which is going to decrease our joint reaction force. And you can see this when people have hip disease, they bend their spine to the right when they have hip pain on the right. They don't bend to the left because that's going to increase the joint reaction force. They bend to the right to decrease that not only joint reaction force but also the moment of inertia, right? Because they're moving it toward the hip. And then finally, let's talk about this picture on the left. How about we have a person at the grocery store and they have 15 pounds they have to carry in their hand. So let's say in the picture in the diagram on figure 4.9 that we're looking at the right hemipelvis and right femur. Okay, I believe that's what we're looking at. Should the person carry the 15-pound grocery bag in the left hand or the right hand to decrease the joint reaction force? Let's assume he's carrying it in the right hand. What is going to happen to W, the line W? Assuming he weighs the same. Where is that going to put the center of mass? So here we see that it's predictably at S2. What is going to happen when we place 15 pounds in our right hand? It's going to move that dot to the right, right? If we move the black arrow, or I should say if we move the black line to the right, then what will the result be? It will be less joint reaction force because we've moved the weight of the body slightly to the right. If, on the other hand, we carry it in the left hand, now we're going to be moving the dot of W to the left. Center of mass to the left, which is going to increase the muscle force. Okay? And it's going to, therefore, increase the resultant joint reaction, right? And that's relative to each other, not just in a static standing position, walking without the bag. So I hope you kind of understand where I'm getting at for those sorts of issues. There will probably be a question or two regarding that in the exam, first exam, just being able to predict what's going to happen in joint reaction forces based on this polygon method. Let's look at page 95. Manual resistance, force, and lever arm. This is a very simple concept. Here in figure 4.18, we have a load placed in the mid-tibia and a load placed at the distal tibia. The load in the mid-tibia is 100 newtons, and the load at the distal tibia is 50 newtons. The load on the left is with an external moment arm of 15 centimeters, and the one on the right, an external moment arm of 30 centimeters. So in that example, okay, the weight is the same. The external torque is 15 newton meters. 100 newtons times 0.15 is 15 newton meters. 50 newtons times 0.3 is 15 newton meters. So that makes sense. What if we change things up a little bit? Let's take the picture on the right, figure 4.18b, and let's say we moved down the leg a little further and increased the force by 10%. What would happen to external torque? You should be able to answer that. How about moving closer to the knee and decreasing by 10%? Same rate. Move closer to the knee, decreasing the force by 10%. What would happen? Okay. How about moving 10% closer to the knee and increasing the force by 10%? What would happen? How about moving 10% further down the leg with 10% less force? And finally, how about moving 20% closer to the leg and increasing the force by 10%? Those should be easily answered. Now let's take a look at our picture of the person pulling the cart. Real quick. There's our guy. Remember, we have to adjust torque here because the angle of pull is not optimized. So coming back here, our picture here on the left of a person doing a manual muscle test on the quadricep at the ankle. Is this optimized position? Okay. In other words, if the patient is producing 100 newtons of force through the quadriceps, is the examiner pushing back with 100 newtons of force? Or is that more? Or is that less? And why? It should be apparent that it's going to be more by the examiner. And why? Because the angle is not optimized. That's why I want to see you guys when you do manual muscle testing, and I'm sure you covered this in your test and measures class. When you do your manual muscle testing, you must be doing it along an optimized line. Okay? It's safer for you, and it gives you the best information. So this person is perhaps 20 degrees off. So we'd have to use a sine of 70, SIN 70 times 100 newtons. That would be what? That would be, so now we have to use a sine of 30 because it's 30 degrees off of the axis of the optimal position, and add that number to the total weight that the person is pushing. So it's going to be somewhere more than 100 newtons of force, not less. If instead of being at 20 degrees off of the axis, off of the 90-degree axis towards the floor, let's say he was 20 degrees off the axis towards the knee, it would be the same. It would require more force by the examiner than the person is actually exerting. All right, so that is part 1 of lecture on biomechanics. Expect lecture 2 coming up. Thanks so much.